everyone. Thanks for joining us. Today, RL Group is excited to welcome Subhojeet for a guest session. Shubho specializes in deep learning and reinforcement learning. He earned his master's degree from the RL AI lab at the University of Alberta, focusing on continual reinforcement learning. He has more than 4 years of experience in researching transformer models and applying them in various areas such as reinforcement learning, language models, multimodal learning, and computer vision. He has worked in research and industry roles at companies like IBM, Y, and Alberta Machine Learning Intelligence Institute. And he also co-founded a startup in the AI field. Currently, he's working as an ML resident at AMI, applying continual reinforcement learning to outdoor active noise cancellation. Today, he'll be presenting his work on AGaLiTe, approximate gated linear transformers for online reinforcement learning. That was published in TMLR this year. Shubho, the stage is all yours. You can get started.
Thanks so much, Rahul, for the wonderful introduction. So today I'll be talking about the work that I did during my master's thesis. So let's get started. So just to give you a rough outline of what this presentation is going to be like, I'm going to start by motivating why we need transformers in reinforcement learning. I'm going to discuss some of the existing transformer approaches and discuss about the computational complexity of these approaches when they are applied to reinforcement learning. I'm going to present the linear transformer architecture, which is sort of an alternative which we are going to build upon in this work. And I'm going to introduce two approaches. The first approach I'm going to call the gated linear transformer. It's going to introduce two modifications. The first modification is a gating mechanism that allows us to control the flow of past information. And the second modification is a feature map that is an alternative to the existing feature maps used in linear attention methods. And the second approach is going to be an improvement upon the first approach, AGaLiTe. So what we are going to do in the second approach is an approximation of the first approach, which would further reduce the computational complexity of the first approach. So before we get started, let's start by introducing the reinforcement learning setting. So all our experiments are going to be in the reinforcement learning setting. And in the reinforcement learning setting, what we have is an agent and an environment. And at a given time step, the agent receives a state, ST, and it takes an action in the world, AT. At every time it takes action, it is presented with a new state and a reward. So the reinforcement learning agent, the goal of the agent is to learn a policy that maximizes the cumulative reward. And the way we learn this policy is using this function called pi, which is conditioned upon the state at a current time step. So what we try to learn is a mapping between the state at a given time step and distribution over actions. However, the assumption in reinforcement learning is that as mapping between the state and the action should be possible, which is not often the case in many real-world scenarios. Instead, what we see is the agent does not have full information about the world. Instead, it observes something called an observation, which only gives the agent somewhat partial information about the world. Examples of this setting could be, let's say, an agent trying to drive a car, or an agent trying to navigate a maze, a 3D maze, or an agent in a 2D world which has limited observability of the entire maze. So agent state construction is a common problem which is studied in this kind of a setting, which we collectively refer to as the partially observable reinforcement learning setting. And in agent state construction in partially observable reinforcement learning typically uses the history of the observations to learn the policy. So instead of using just the observation at a current time step, we condition the policy on the previous set of observations. Alternatively, one can use a recurrent state update function to maintain a summary of the past. So what we can define instead is a state update function U, which at a given time step ingests the current observation and the previous action and returns an approximate state. The agent can then use this approximate state instead to condition a policy. Common approaches to implement the state update function are RNNs. So RNNs such as gated recurrent units and long short-term memory architecture has been used very commonly to learn the state update function. What the RNN update work, the way RNN update work is it has some hidden state HT-1, and at a given time step, it uses an observation to update its hidden state to HT. RNNs have been used commonly for agent state construction in actor-critic algorithms. For instance, here I'm demonstrating an RNN being used in a vanilla actor-critic algorithm where the observations are fed sequentially to the RNN, and the output of the RNN is used to generate a prediction from for a policy and also a prediction for a value function. However, transformers have recently gained a lot of popularity. In 2017, there was this paper, Attention is All You Need, and then suddenly there were so many papers which were discussing this approach, which brings us to the question, why don't we see transformers that much in RL? And the key idea in transformers was to use multiple layers of deep neural networks. And the idea is that each of these layers learn hierarchical patterns in the data. And in each of these layers, you have multiple self-attention heads, which capture diverse relationships in the data. But then the question is, why don't we use transformers that often in reinforcement learning? And the short answer to that is they are computationally expensive for this task. So, and this has to do with the way RNNs process data versus the way transformers process data. So an RNN processes data sequentially. So let's say you have an input, a sequence of inputs, and RNN would process data one at a time. So the first time step, the input would be processed, and then it would result in a hidden state, and sequentially, the next time step would process the rest of the input one by one. On the other hand, the transformer processes the entire input sequence in parallel. So instead of encoding the input sequence one at a time, you concatenate everything as a matrix, and then you pass it to the self-attention layer to get an output as a matrix, which should contain the sequential information for the entire input sequence. So this was sort of useful in supervised learning. In supervised learning, the data is available offline, and processing the entire input sequence in parallel is making sense because we can leverage GPUs. But in reinforcement learning, that is not the case. In reinforcement learning, the data is generated through interaction with the environment. So every time steps data is dependent on the previous time steps representation. And we need to process data sequentially in the reinforcement learning setting. And the input sequences can only be processed up to the current time step. But why do we want to use transformers in reinforcement learning? And the reason for that is that self-attention mechanism seems to work really well in long context. And we can already see that being applied to the text domain, where we see like ChatGPT being able to handle millions of contexts all at once. Whereas it has been noted previously that RNNs and LSTMs, RNNs such as GRUs and LSTM, tend to fail at long contexts. And there have been some experiments which show this. So as you increase the context size, context size for a given experiment, the LSTM and RNN start to fail after a while. Also, self-attention is parallelizable. This could be useful for certain RL algorithms such as PPO, which often train on a sequence of data. So we can leverage, if we have an architecture which is parallelizable over a batch of input, this could be useful to increase the training pipeline, to increase this efficiency of the training pipeline. So the motivation for this work is, can we make transformers efficient for reinforcement learning? And more specifically, how do we efficiently process sequential data with self-attention? So just to give you a background, we're going to start by introducing vanilla self-attention. So as I mentioned before, self-attention, the vanilla self-attention in the transformer architecture operates on matrices. So let's say you have an input matrix of size n cross d, where n is the input sequence length and d is the embedding dimensionality. Self-attention architecture would output a matrix of equivalent dimension, n cross d, where where the output matrix capital A is going to contain the sequential information about the different parts of the input sequence. And under the hood, what self-attention does is it operates on this input matrix X, and it calculates three different matrices called the query, key, and value matrices. It then calculates the attention output A, capital A, as the softmax of the dot product of the query and the key times the value. So the key takeaway here is that in self-attention, we are operating, the assumption is that the input to the self-attention layer is a matrix, and all the operations are done on matrices. So how is self-attention applied to streaming data such as reinforcement learning? The previous work which has done this is called the Gated Transformer XL paper, which was a paper by Google. And the idea was very simple, that you maintain the past history of inputs as the context of input to the self-attention layer. So instead of having the entire input sequence, what we can do is, if we are applying self-attention in a sequential fashion, what we do is we maintain a rolling window of the history of the past inputs. So let's say M is an hyperparameter that controls the number of inputs that we are storing. So we maintain the last M inputs along with the current input at the current time step to calculate the self-attention. So we concatenate the current time steps input with the history of the past inputs and use that to calculate the self-attention output. The main challenge for this kind of approach is that the theoretical context length for this architecture, that is how far the transformer architecture can look back in time, depends on two hyperparameters, capital M and capital L. The M being the number of inputs that you are willing to store as a context, and L is the number of layers in the transformer architecture. So the computational complexity then is proportional to the amount of context that you are storing. The space complexity becomes M times T, and time complexity becomes capital M times T squared. So your computational complexity is dependent on the amount of context that you're storing in the history. And this is a challenge because increasing the context would result in increasing computational complexity. So every time you want the transformer architecture to look back farther in time, the only way to do that is by increasing the computational complexity. So let's try to demonstrate that problem by performing a simple experiment in a partially observable RL problem. So let's try testing out GTrXL in a partially observable RL setting. So we're going to start by testing out in this environment called the T-maze. So this T-maze environment, the idea is that the agent starts in a bottom of a T-shaped maze, and the agent is shown a binary Q signal at the beginning of the episode. The agent then travels through the corridor and has to take an end at the end. The agent has to take a turn at the end of the tunnel, and the right tunnel that the agent must take depends on the initial Q signal that the agent receives at the beginning of the episode. So, for instance, I have two examples here. In the first episode, what is happening is it's shown this Q01, which means the reward is in the left turn at the end of the intersection. On the other example, I am shown initial Q signal of 10, which says that the reward is on the right turn at the end of the intersection. So the Q signal is only shown at the beginning of the episode, and then it does not see the Q signal ever again. And it has to remember this Q signal in order to take the correct turn at the end of the intersection. So the agent's observation space is 18-bit, and it's a binary observation space. So the first 2 bits encode the Q signal, which is 0, 1 or 1, 0 only at the first time step of the episode, and it's 0 otherwise. The next 8 bits encodes the agent's position in gray code. So everything about this world is fully observable except the initial Q signal that the agent receives at the beginning of the episode. And then we have also a few distractor bits. We have 12 to 17 bits of distractor, which is just randomly generated binary numbers, just to confuse the agent. And then we have 4 actions that the agent can take: left, right, up, and down. And the experiment framework is as follows. We're going to use the advantage actor critic framework. We're going to train each agent for 10 million time steps. And we are going to present the performance of the agent as the mean success rate in the last 100 key time steps of training. Success rate being the number of time the agent takes the correct turn. So if you think about it, a memoryless agent, an agent which does not remember the initial Q signal, has a 50% probability of taking an incorrect turn. So it has a success rate of 0.5. So an agent which does not have any memory should at least get a success rate of 0.5. And an optimal agent should get a success rate of 1.0, which means every time it is able to remember the Q signal and take the correct turn. So, the first experiment we are going to do is going to ask this question: does the GTrXL architecture need the entire history in order to solve this simple problem? And so the experiment we're going to run, we're going to vary the corridor length. So if you remember, in that T-shaped maze, we had a corridor where the agent has to travel through. So we're going to change the corridor length from 120 to 200. Just to have this keep a side note here, the theoretical context length of GTrXL was big O of M times L. And we're going to train 2 agents. So the first agent we are going to train is going to have a memory of length 256, so which means it's going to store the last 256 time steps as input. And the second agent that we are going to train is going to have a memory of the last 128 time steps. So theoretically, both these architectures should work across all the corridor lengths that we are testing for, because the first architecture, if we do M times L, so we are using 4 layers in both the architectures. If we do M times L, it has a theoretical context length of 1024. And the second architecture has a theoretical context length of 512. However, our hypothesis is that GTrXL would need the entire history of inputs in order to perform well in this problem. And this is exactly what we observe. So we train the 2 architectures. What we see is that in order to perform well in this problem, even though the context length for each of these architecture is above 512, above 200, we are not able to see that GTrXL 128 performing well in this problem. It needs the entire history of the episode in order to do well in this problem. So GTrXL 256 literally has the entire episode as in its input, and it's able to do well in this problem, which is sort of a challenge, because even for the simple problem, just to remember 200 time steps, we had to store the last 200 time steps of input data as an input to the transformer architecture, and it only becomes harder and harder if you want the agent to remember for even longer time steps. So yes, just in conclusion, both architectures had the theoretical context length way above the largest corridor length. But in T-maze, we see that even in the simple problem, we see that GTrXL needs the entire history provided as input in order to do well. And this is bad because increasing the amount of history increases the computational complexity. And in most problems, we can't store the entire history in the state. But turns out RNNs don't really have this problem. RNNs offer a context, what we call is a context independent inference cost. So the question is that, can we have an RNN that resembles the transformer self-attention architecture in some way? So turns out in 2020, there was exactly a paper which tried to answer this question, and they had this work was called Transformers are RNN, and what they proposed was an alternative to the self-attention mechanism, which works sort of like a recurrent neural network. So they call this architecture the linear they call this approximation the linear self-attention mechanism. And this is an RNN which approximates self-attention. And the idea was that instead of using softmax to calculate similarities, as we do in a vanilla self-attention mechanism, we instead introduce this notion of a kernel function. So a kernel function operates between, is a function defined between two vectors. And the idea is that given two vectors, it does a dot product of those vectors using some feature map phi in order to calculate a scalar similarity value. And the definition for this feature map phi is that it's a non-linear feature map that outputs positive features. So the change that happens from a vanilla self-attention to a linear self-attention then a layer is mechanically is that the input could now be processed sequentially one at a time, and the state that the agent the state that the self-attention layer now uses is of fixed size. So instead of having a hyperparameter m, which is the number of time steps back we want the agent to look back, right now for linear self-attention, the recurrent state is a fixed site and it is not dependent on the number of previous inputs. And internally, the way linear self-attention works is somewhat similar. You do generate the key query and value. You do generate key query and values, but instead of generating key query and values on the entire input sequence all at once, you just generate key query at a given time step. You can do it sequentially. You generate the key query and value just for the input vector at time step t, and then you update a recurrent state in an iterative fashion at each time step, using the information just from the current time step and using information just from the current time step. And then you calculate the attention output as a function of this recurrent state and the query vector that you generate at the current time step. So in theory, it seems like linear transformer is an RNN. It provides equivalent self-attention mechanism. It does not require storing the past inputs, and it stores the history as hidden states instead of directly storing the entire input sequence. And it has a context-independent computational cost. So seems like we have an RNN already that resembles a transformer. So does that mean the problem is solved? Can we just apply this architecture? Well, not really. There are some challenges to the linear transformer mechanism that we are going to address in this work. So the key challenges that prevents the application of linear transformer in RL are the following. The first challenge is that the recurrent state update function, which is defined in the linear transformer architecture, naively adds positive values to the recurrent state. So the recurrent state update is defined as follows. First, we have this matrix capital CT, which adds another matrix coming from the current time step, and another state vector ST, which is again positive values are just added naively to the recurrent state. So there is no notion of position in the naive recurrent update. The second is that an explicit feature map needs to be specified. So earlier I said that the feature map phi outputs positive value, but the problem of linear transformer is that this choice of feature map affects the performance by a huge margin. The third problem is that in the linear transformer architecture, we are still maintaining a matrix as a recurrent state, and the quality of the performance of the linear transformer architecture depends a lot on the size of this matrix. And if you reduce the size of this matrix, its performance degrades. But storing a matrix for for each of the heads of the transformer architecture is computationally expensive, because typically transformer architectures use multiple self-attention layers and multiple self-attention heads. So if you want to use really large architectures sequentially, having a recurrent matrix for each of these self-attention heads is going to be computationally expensive. So we propose 3 modifications which try to solve each of these challenges. The first one is the first 2 modifications we collectively refer to as the gated linear transformer. In this, to address the first challenge, we propose a gating mechanism that controls the flow of past information. To address the second challenge, we propose a parameterized feature map that attempts to directly learn the feature map from data. And to solve the third challenge, we propose an approximation to the AGaLiTe's recurrent state update, which does not require storing a matrix. Right. So we're going to start by solving the first challenge, which is the recurrent updates in the linear transformer architecture naively add positive values. So just to go over the recurrent state update function again, in the linear transformer architecture, we define this recurrent state update, which directly adds values to a recurrent matrix and a vector. And to solve this, what we introduce is a gating mechanism. So we introduce additional learnable parameters into the network, and then we use the sigmoid function to generate gating values between 0 and 1. And then we use these gating vectors to control the flow of past information. So the idea is very similar to the way LSTMs are implemented. So we generate the gating values using the input sequence, and then we use that to control the flow of past information. There was a question in chat. Rahul, can you repeat that again?
I was just asking, what's this CT and KT?
Right. That's a good question. So KT is the key vector for the current time step, and CT is a recurrent matrix that you generate as a function of your. So your CT is a recurrent matrix that you generate as the sum of the outer products of the value and the key vector.
Okay.
Right. So, and the second challenge was that we need a feature map in order for the linear transform architecture to work well. And this feature map exists when we are trying to generate the query and the key vectors for a given time step. And the way this feature map is applied is we use the regular WQ and the WK matrix in this transformer architecture first to generate the initial query and key values, and then we apply this function phi on top of it to generate the feature, to generate the final query and key values. So in the linear transformer architecture, the way they define feature map is that it serves 2 purposes. Given an input vector, we want first the feature map to non-linearly transform the input vector, and second, we want it to project the input vector to higher dimensions. But existing methods typically use the element-wise functions such as ReLU or ELU, which only non-linearly transform the input vector, but they don't project the input vector to higher dimensions. There have been other methods such as random features, which try to approximate the softmax kernel. These approaches also will do both the things. They will non-linearly transform the input vector. They also project the input vector to higher dimension. However, they use randomness as a way to do this approximation, which introduces variance. So the challenges of the existing methods are that both of these methods have been shown to have limited memory capacity in existing work. And additionally, if you use random features, they introduce variance, which make it harder to learn. So in our work, we propose a deterministic approach to learn the feature map directly from the data. And to do that, we introduce more additional parameters that we are going to use to learn the feature map. And we are going to introduce a hyperparameter called ETAP that is going to control to what dimension we want to increase the input feature map to. And this is going to ultimately control the size of the recurrent state that we are going to use. So instead of, so the size of the recurrent function state is now going to be d squared times eta, the size of the matrix, recurrent matrix, and the size of the recurrent vector st minus 1 is going to be eta times t. And the way this feature map is implemented is using an outer product operation. So using the introduced projection matrices, we calculate an additional vector that we will use to do an outer product with our query value to generate and then flatten it in order to generate a vector of higher dimension. So the idea behind this feature map is that you sort of try to learn how to project the input vector into a higher dimension. We implemented that using an outer product operation. And we do the same thing for the key as well. So we implemented the same thing for the query and the key. And in order to, we also adjusted the gating mechanism accordingly in order to have to match the dimensions of the introduced projection map. So yeah, let's look at how this approach will perform in the real world. So we are going to start by experimenting this new approach called gated linear transformer, which introduces these two modifications, a gating mechanism first to control the flow of past information, and the second is a feature map to learn the feature map directly from data. And then we're going to, so let's run a second experiment to test how AGaLiTe will do in comparison to GTrXL in the TMAs problem. So we'll train a AGaLiTe agent with eta equal to 4 in TMAs. Additionally, we'll also add some of the earlier architectures such as GRU and LSTM as a baseline. And our hypothesis is that AGaLiTe, despite not having the entire history of observation in its recurrent state, is going to be more is going to match the performance of GTrXL while being more computationally expensive. And also, we are predicting that LSTM and GRU will fail at large corridor lengths. And this is in fact what we observed. So what we see here is we'll start with LSTM and GRU. LSTM fails at all of the corridor lengths. It's not able to solve any of the corridor lengths that we tested for. GRU performs well initially, but at around corridor length 180, it starts to drop massively. On the other hand, our proposed architecture, so initially the architecture was called AGaLiTe. That's why there's a name. The name is incorrect here. But what I want to show here is this line here shows our architecture, and it's able to match the performance, get close to the performance of GTrXL 256 across a range of the corridor lengths. Just to give you a perspective, AGaLiTe uses 40 times less operation and 1.96 times less space than the GTrXL 256 in order to solve this specific problem. So we were able to show an architecture which performs close to the GTrXL 256 agent despite using a recurrent hidden state. And it has lesser computational requirement, both in terms of space and time, than the GTrXL 256 agent in the TMAs problem. The third challenge, now we will try to address the third challenge, which is that we maintain a matrix as a recurrent state. Yes, so we use 50 guns in this in each of these experiments. So all of these experiments were evaluated across 50 runs, and we performed extensive hyperparameter sweep for the entropy and the learning rate. So the third challenge is that we maintain a matrix as a recurrent state. So if we look at the improvement in terms of space complexity, we only improved it 2 times. So maybe if we, and maybe we can improve it further if we try to do some approximation that does not require storing a matrix as a recurrent hidden state. So we're going to look at that third problem. And the challenge is that this operation is defined on matrices. So this recurrent state update, CT, at a given time step is using the previous recurrent state CT minus 1 plus some matrix that we calculate at the current time step. So we're going to use, and this is going to be a challenge because transformer architecture consists of multiple self-attention heads. And for instance, the vanilla transformer architecture, which was proposed in the 2017 paper, itself contained 48 self-attention heads. And if you think about architectures which is common nowadays, like GPT-2 and things like that, they have much larger number of self-attention heads than what we had previously. And so we need to reduce the space requirement. And to do that, what we propose is to derive a low rank approximation of the recurrent state update function. So I'm not going to go into the detailed derivation of the recurrent state update function, but just to give you an idea of how it works, we are going to, our proposed approximation is derived using the trigonometric representation of the Kronecker delta function. More details about the derivation could be found in the paper in the appendix. So the change is going to be as follows. The original recurrent state update function was operating directly on matrices. So we had some previous recurrent state and we're adding some values to the previous recurrent state. We're going to instead propose an approximation. So let's say there is an approximation C tilde T, which is a rank R approximation of capital C T. And this rank R approximation is denoted using sum of outer products of some value and query vectors. And the way we are then going to redefine our calculation is that instead of directly calculating the matrix as an outer product and directly operating on the matrix, we instead operate on these value vectors. We instead store the value vectors as recurrent states and update these value vectors as in order to calculate the recurrent matrix at a given time step. So the change that happened from the original recurrent update to the new recurrent update is that we no longer require storing the entire matrix. Instead, we can store, depending on the rank that we choose, we can store a bunch of vectors as a recurrent state, and then we update on those vectors to calculate the recurrent state update. So then the self-attention mechanism changes as follows. Instead of using the matrix as an input, we now have as input vectors, and the number of vectors that we have in the self-attention layer is going to be controlled by this hyperparameter R. So the question is, so then we're going to explore how well this approach performs, again in the setting that we presented earlier. So the question is, can we match the performance of AGaLiTe that we presented earlier in TeamAge? And we are going to train an AGaLiTe agent with eta equal to 4 and R equal to 1. So we are going to start with the worst possible approximation and see how well that performs. So our hypothesis is that even with the worst possible approximation, that is R equal to 1, we will be able to perform similar to AGaLiTe in TeamAge. And that is what we observed as well. So AGaLiTe with eta equal to 4 and R equal to 1 is able to match the performance of AGaLiTe in this problem. And to give you a perspective now, we are using 125 times less operation and 36 times less space than the GTrXL agent. So this is a huge improvement from the transform architectures which are commonly used in the reinforcement learning setting, while having very similar performance in this environment. So in conclusion, we were able to match the performance of AGaLiTe even with even when the approximation hyperparameter is really small, and the computational requirement of AGaLiTe is much less compared to both AGaLiTe and GTrXL. And I'm not going to go into the details of the computation complexity, but the thing that I want to highlight here is that in GTrXL, we had this hyperparameter M that was controlling the number of inputs that you store as your history. But in in AGaLiTe and GaLiTe, we don't really have that anymore. Instead, we just have some hyperparameters which are statically defined, and they do not depend on the number of on the size of the input sequence that we're using. So potentially, the context length for such an architecture is possibly theoretically it is infinite, but in practice we don't always observe that. But just to keep a note of that. So we tried also testing our agent in more realistic settings, and we started with the pixel-based navigation task called the memory maze. So this is an the mystery path. So this is a very interesting problem setting. So in this problem setting, the agent's observation is what I'm showing here on the right-hand side. So here you have like a blue box and a green box. The agent's goal is to reach this green box. But the path that the agent must follow is not visible to the agent. So the true path is shown here. This path that I'm showing on the left-hand side is not visible to the agent. So every time the agent travels and it is off its path, the episode does not end. What happens is the agent is reset back to the blue state. And it is shown a visual feedback as a cross symbol. So the agent has no idea what the path is like, but it must remember through this visual feedback and failing a multiple number of times that okay, if I fell from this region, that means I should not probably go there when I try to navigate the maze again. So the agent has to try to remember the locations where it is falling, and next time it tries to navigate, it has to incorporate that information in order to reach the goal state. And what we found is that in this problem setting, our approach is able to outperform the transformer architecture while using much less computational complexity across both variants of this environment. So we tested on the mystery path grid and the mystery path. The mystery path grid was more of a grid world kind of movement, allowed for a grid world kind of movement, whereas the mystery path was allowed for more pixel-based like game kind of movements. Additionally, we also tested on the memory maze environment. In the memory maze environment, the agent has to navigate this 3D maze where it has to remember key information about the different objects that it sees in the environment, and it has to use this environment to reach different goal states. And this environment is 3D, and we observed that in terms of performance, we are able to match the performance, get quite close to the performance of a transformer agent while having more training efficiency. So in terms of frames per second and GPU memory usage, we have improvements. Lastly, we also tested on a more generic setting called the Crafter. This is a 2D adaptation of the game Minecraft, in which the agent has to navigate a really large maze and solve generic problems. And what we observed is that our agent is able to outperform the transformer agent and also previously reported baselines in this environment. So in conclusion, we present a recurrent alternative to the transformer architecture that builds upon the linear transformer architecture. Our first approach is called the gated linear transformer, which addresses two key issues in the linear transformer self-attention mechanism. The first is that it proposes a gating mechanism that allows it to control the flow of fast information. And the second is that it proposes a parameterized feature map, which is an alternative to the existing feature maps used in linear attention methods. Our second approach is improving upon the first approach, and it approximates the GaLiTe's self-attention mechanism and further reducing the computational complexity. Finally, we show that in a diagnostic partially observable RL environment called the T-maze, we show that the XL self-attention requires the entire history as input to achieve good performance. On the other hand, GaLiTe and AGaLiTe are able to match the performance of a more computationally expensive transformer architecture with much more computational efficiency. Additionally, we also provide results in pixel-based environments called the Mystery Path Memory Maze and also the open world survivor game called Craftax. I would like to thank the collaborators in this work, PhD student Esra, and my advisors Adam White and Marlos C. Machado. Thank you so much, everyone, for the presentation. I'm looking forward to your questions.
Really interesting, Doc.
Thank you.
So, are there any limitations for the current approach, like AGaLiTe?
Right. So in terms of limitation, I would say that during the time I was doing this work, there was also a lot of work being done in parallel with respect to state space models. And when I finished my master's thesis, there was a paper which applied state space models to reinforcement learning. I would say, like, if I was to start a project right now and I wanted to use as efficient architecture for reinforcement learning, I would probably go with state space models because they don't require introduce. So in order to, in my work, what I had to do is, in order to match the computational efficiency of transformers, I had to propose a lot of gating mechanisms and these kind of mechanical ways of matching, like the performance of the transformer architecture. On the other hand, state space models are more simplistic and they come from a they come more from a theory standpoint, and they have like they're showing matching the performance of these architectures using much simpler approaches. So I would say like they are more suited if you have to think about like in terms of simplicity, at least, like this approach is probably a little bit more complicated than state space models. Also, real-time recurrent learning is another interesting direction, which I wanted to explore during my master's research. And with state space models, it was recently shown that it is possible to apply state space models in a recurrent fashion while also calculating the gradients in a recurrent fashion. So you don't have to use truncated backprop. You can also calculate the gradients in a recurrent fashion, which might be a bit difficult for AGaLiTe to calculate the derivations for the recurrent state update. So the recurrent gradients for AGaLiTe would be a bit more difficult.
Makes sense. Any other questions? Yeah, so if there are no other questions, we can wrap the session. We can thank the speaker. And then if you have any questions, Jack, you can definitely reach out to him offline, right?
Thank you so much.
Yeah, thank you, Subho, for joining us today. It was a great session. Thank you.
Thank you, Rahul, for organizing this.